Hello everybody, welcome to part 5 of our series. In today's part, before applying the concepts that we have learned in part 4 and part 3, we are going to learn a very important concept, which is how to feed a large amount of data to our model, considering the limitations of the device that we are working on. So this is going to be a very important part of our series. So let's get started without wasting any time. So this part of our code does data pre-processing, and I have already explained it in part 2. So today let us start from here. So here I have defined two variables which are batch size and time steps. So batch size is 256 and time steps are 180. So this means that our group of data will contain 256 sequences and each sequence will have 180 data rows. So when I say data rows, it means that this is the first data row, this is the second data row, and so on and so forth. So our model will at a time take 256 sequences, whereas each sequence will have 180 such data rows. So now even if we distribute our data in groups with the help of batch size and time steps, it seems to be a large amount of data. So what we will have to do is we will have to find out another way to fed data in small chunks. So here we have variable training data generator, and this variable stores the object of class training data generator. So this training data generator is a custom class that I have written here, and it is derived from base class sequence. So this sequence class is provided by Keras package. Now this sequence class already has some methods predefined in it, and we have to customize those methods according to our needs. So for that, we will override some default methods, and to do that, we have to write the name of the predefined method here and start it with double underscores. So here, as you can see, this init method starts with double underscore. So this method is actually written in the sequence class, but I am customizing it according to our needs. So this takes these parameters, and let us understand them one by one. So the first parameter is known as self, and it is very important. So to understand this self parameter further, we will have to understand this data parameter. So now, as I had told you before, we cannot feed all the data to the model at once because we have some limitations due to our computer memory. So for that, this training data generator will fetch the data on the fly from this CSV file. But to do that, it needs to create multiple instances of itself. So let us say that the first instance of this class stores data ranging from first data row to the 10th data row, and the second instance of this class stores data ranging from 11th data row to the 20th data row. So now for the first instance, the mathematical calculations that I have performed in this last line and also the data stored in these two variables will be related to the data set ranging from first data row to the 10th data row, as this is the first instance. However, for the second instance, the mathematical calculation performed in this last line as well as the values stored by these variables will be related to the 11th data row to 20th data row of our data set. Now this instance management is performed by Python internally, but for that we will always have to pass this self parameter to the functions that need to be tied to a specific instance of the class, like this one, and then we will have to define the variables from this self parameter itself, like I have done here, so that these variables are picked up from specific instances on the fly. So now let us move to the next parameter, which is workers. So this parameter defines how many parallel threads we want to spawn, which will perform the task of fetching the data and giving it to the model while training. And this variable next to it use multiprocessing, which is a boolean which defines whether we want to use multiprocessing or not. So actually, if we set workers to more than one and we set this to false, then it's of no use. To use the actual power of parallel computing, we will have to set workers to more than one and also this boolean to true. So now let us move to our next parameter, which is max queue size. So this max queue size defines the number of batches of data that should be loaded in the memory all at once. So for example, here it is 10. Then this means that by default it will load 10 batches of data all at once in the memory. So these batches will be queued to be provided to the model one after the other. So by the way, these values that I have provided here to the parameters are the default ones, and these can be changed when needed. Now, these two parameters here, batch size and time steps, those are nothing different that I have explained you, and these are used to specify how the data in groups will be distributed and fed to the model. So here by default batch size is 32 and time steps are 60. So this means that by default 32 sequences will be provided to the model at once, and each sequence will be 60 data points long. And also, if we now go back to max queue size, then this means that 10 such groups of 32 sequences will be loaded in the memory all at once, and they will be fed to the model one by one. So now once we know what these parameters mean, let us move forward and understand what this function actually does. So here first we have called the original copy of this function, that is pre-written in this base class. So we will pass workers, use multiprocessing, which is a boolean, and max queue size to the original copy of this function inside the sequence class. Once that is done, we will move forward and store these parameters inside these variables which we have defined here. So we will store the parameter data inside the data variable which is defined here. The parameter batch size will be stored in the variable batch size, and the parameter time steps will be stored in the variable time steps. So once that is done, we will define another variable called indices. Now here we are performing some mathematical calculations, and these mathematical calculations will help us to create an array which will be stored in this variable which is indices. So now let us understand what does the array store. So let us say that we have a data set of 1000 data rows. So the first data row will be indexed as 0, the second data row will be indexed as 1, the third data row will be indexed as 2, so on and so forth. So here we will have 59, then 60, then 61, and 62, so on and so forth until 1000. So here we have 1000. So now let us say that our time steps are 60. So t is equal to 60, and now let us start from 0, that is the 0th index. So now when we will start from 0th index, we will land up on 59, and the number of data rows we will then have will be equal to 60. So we can say that this is our first sequence, and it will have 60 data rows since our time step is 60. So now if I ask you that what is the starting index of this first sequence, then you will say that it is 0. So this is the starting index. So let us represent it by SI. Now again let us start from 1 and count 60 data rows, then we will land up on 60. So this is yet another sequence, and again if I ask you that what will be the starting index of this sequence, then you will say that it is 1. So let us again represent it by SI. Now similarly, if we start from 2, we will land up on 61 and we will have again 60 data rows, and again 2 is the starting index. So this is what the array stores. It will store all the starting indices of all the sequences which will be defined by our time steps. So in this case, it will store 0, 1, 2, 3, and so on and so forth until it has found out that no further sequence can be made. So for example, here we will have 9, 9, 9. However, it won't store this 999th index in the array since no sequence can be formed as there is only one data row remaining. Similarly, it won't store 998th index or 995th index since no valid sequence of 60 data points can be formed from either of these indices. So how does it calculate these starting indices of each sequence is actually pretty simple. It will take the length of the data set. So in this case, it is 1000, and then it will subtract time steps from it. So 1000 minus 60. And then once that is done, it will also subtract -1 from it. So what we'll have here is 1000 minus 60, so that is 940, and 940 minus 1, that is 939. So actually we have calculated the starting index of the last sequence possible from the dataset of 1000 data rows, and it is 939. Now obviously if this is the starting index of the last sequence possible, then there must be some sequence possible if we consider 938 as the starting index, and it will range from 938 to 998. So to check out this, we can add 60 to 939 and then we will get 999, and if we add 60 to 938, then obviously we will get 998, which is just before this. So once it has found out 939 as the starting index of the last sequence possible from the given data set, then it will subtract 1 successively until it has reached 0, and it will add all the numbers that it had found out to the array. So 939, 938, 937, 936, so on and so forth until it has reached 0. So all these indices represent starting index of one or the another sequence, and those will be stored in this indices array. So now if you will see here, length of data minus the time steps. However, I have not written here -1. This is because it will by default start from the value which is 1 lesser than the result of this operation. Now let's move forward and understand the next method. So as you can see, its name again starts with double underscores and ends with double underscores. So the original version of this method again is defined in this base class sequence, and we are customizing this method according to our needs. So here we only have one line of code, and let us understand what it does. So first we are fetching the length of the indices array that we have declared here, and once we have that, we are dividing it by batch size. So again, let us understand what is actually happening here. Now, as I told you before, this indices array stores the starting indices of all the sequences possible in the given dataset and with the given time steps. So in case of our example, it will store 0, then 1, then 2, then 3, and so on and so forth until 939. So 939. Now if you count this, this will be equal to 940 elements. So this array will have 940 elements, and this actually represents the number of sequences possible in the given dataset. So it is actually very logical. Since it stores only starting index of all the sequences possible, then naturally the number of starting index present in this array will be equal to the number of sequences possible. So when we fetch the length of the indices array, it will return 940 in this case, and now our batch size is equal to 32. So let me divide it by 32. So it will give us something like 29.37, and actually the part after the decimal doesn't matter. Since we have written here np.sil, it will round up this value, and instead of 29, it will return 30. This np.sil always rounds up the value and it never rounds down. So it will always return the value which is greater than this actual number. So here we will have 30. So here this function will return 30. Okay, so now once we have understood this, that what does this function returns and how does it return, it is also important to understand that what is this 30. So this 30 represents the number of groups of data possible from the given data set. So this is also known as number of batches of data possible from the given data set, given the number of time steps and the batch size. Now the batches should not be confused with the batch size, as batches are nothing but groups of data, and batch size are the number of sequences that we are feeding in one group, and time steps is nothing but how long each of this sequence will be. So now if this function here returns 30, then this means that there will be 30 groups of data. Each group will have 32 sequences since our batch size is 32, and each sequence will have 60 data rows since our time steps are 60. So that is what this function does. So before going any further, let us first try to visualize this hierarchical grouping of training data so as to understand it more clearly. So first there are groups of data. So let me represent it by letter G inside this box. Then each group will have certain number of sequences of data. So let me represent it by S, letter S inside this box. And the number of sequences inside each group will be equal, and those will be equal to batch size. So in this case, the batch size is 32. So each group will have 32 sequences. And now each of this sequence will have certain number of data points. So let me represent it by letter D inside the box. So the number of data points will also be equal in each sequence, and those will be equal to number of time steps that we have written in our code. So those are 60. And now there can be number of groups, each group containing number of sequences and each sequence having number of data points or data rows. Now the number of groups is actually not decided by us, and it is decided by the code itself. And so let me represent it by C. So here, as you can see, this len function is what decides the number of groups, as I had told you before. Now let us move to the next function, and again, since it starts with double underscores and ends with double underscores, it means that original copy of this function is predefined in this base class, and we are just customizing it according to our needs. So first of all, we have declared a new variable called batch underscore indices, and this stores an array which is derived from the original indices array. So to understand this slicing part, let us go back to our whiteboard. Now we know that our original indices array has the following elements: 0, 1, 2, 3, dot 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 59, then again 60, 61, so 61, and dot 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 till 939. So the original indices array is made up of these elements. Now let us first check the parameters that this function takes. So it takes the first parameter as self and the second parameter, which is index. So now for the first instance of this function, the index will be 0. For the second instance of this function, the index will be 1. For the third instance of this function, the index will be 2, and so on and so forth. So that's why passing this first parameter as self is very important here. And now let us say that for the first instance, the index is 0. So for the starting part, we have 0 multiplied by self dot batch size, which is defined here. So it will be 0 into self dot batch size, which will return 0. Okay, so since we are slicing self dot indices, we will start from 0 here for the first instance of this method, and then let us see what does this ending part does. So index plus 1 into self dot batch size, that means 0 plus 1 into self dot batch size. So 1 into self dot batch size, so it will return 32. So this means that it will start from 0. So this is our starting part, and then it will end at 31st. So let us say that this is 31st index. So now this, from starting from 0 till 31st, will have 32 indices. So this much part will be stored in new array called as batch indices. So bi, and this will be stored for the first instance. Now let us say for the second instance, this method is called again, but when it is called again, this index variable will no longer be 0 and it will be 1. So now when it is 1, the starting part will return 1 into self dot batch size. So 1 into 32, so it will return 32. So now let us say that here we have 32. So this will be our starting index, and the ending part says index plus 1 into self dot batch size. So 1 plus 1, that is 2 into 32, which will return 64. So let us say that here we have 63, and here we have 64. So now it will start from 32 and it will end at 63, and thus it will complete yet another 32 elements. So now as you can see, we have made two groups from the elements present in our original indices array. So these indices ranging from 0 to 31 for the first instance will be stored in our batch indices, and for the second instance these indices ranging from 32 to 63 will be stored in our batch indices. So what we are actually doing is we are grouping these elements present in the indices array, and each group of these elements has 32 indices. So this belongs to first group of data, this belongs to second group of data. So these 32 indices will be stored in the first group of data, and these 32 indices represent the starting indices of 32 sequences, and each sequence will be 60 time step long. So now you must be understanding how this hierarchical grouping works. So for the next instance, that is for the next group of data, another 32 indices will be chosen. However, they will be exactly after the first 32 indices that were chosen before, and thus we will have next 32 sequences while we will be feeding our model the data for training. So this is how it works. Okay, so now let's get back to our main function. So once we have our batch indices ready, we will pass the batch indices array to data generation function. And as you can see here, this data generation function is defined here. By the way, if you have noticed, this data generation function has double underscores at the starting. However, it doesn't have double underscores at the ending, and hence no copy of it exists in the base class, that is our sequence class. So this is a completely new function that I have defined here. And as you can see, it returns two arrays, x comma y, and these two arrays will be stored in these x comma y variables of getItem function. And once this is done, we will return these two arrays through our getItem function. So now let us understand what this data generation function does. Now first thing that we are doing inside this function is we are creating two empty arrays, as you can see here, np.empty, so numpy.empty, and we are storing them into separate variables, so x and y. However, we have assigned some shapes to these arrays, and these shapes will be assigned to these respective arrays in spite of they being empty. So now let us understand the shape of the first array. So here as you can see, first there is the length of batch indices, then time steps. So time steps are 60, and then self.data.shape. So when we write self.data.shape, it will return us the shape of this data array, and this data array is nothing but this parameter that we have passed here. So it will be again tied to the instance of the class, and so we need this self parameter here also in this data generation function. Now why we have assigned this particular shape is, as I told you before, we will be going to use LSTM model to predict the prices of Bitcoin. So LSTM model while training needs input in a specific format. So the array that will have the training data and which we will feed to our model must have the shape of batch size, then time steps, and then number of features. So now let us understand the shape that I have written here. How does it correlate to the format that I told you just now? So now, just some time before, I told you that our batch indices array will have these elements, and depending upon the instance, it will have either the first group of elements or the second group of elements, and then third group and the fourth group, and so on and so forth. However, it is interesting to note that the number of elements that will be stored in this batch indices array will be equal to the batch size that we have specified. So as you can see, since the default batch size is 32, and in this example I have taken the default batch size, so per instance the number of elements stored in the batch indices is also 32. So for the first instance it will be 32 number of elements inside the batch indices array. For the second instance again it will be 32 number of elements inside this batch indices array, and it will go on so on and so forth. So this means that the number of elements stored in this batch indices array is directly equal to the batch size. So that's why here we have written len in brackets batch indices. So this will fetch us the length of the batch indices array, which is nothing but the number of elements stored inside this array. So now once that is done, here we have already written the time steps, and this is referring to the variable that we have declared here. So again, once this is done, here we have self.data.shape. Now let us see how this self.data.shape correlates to the number of features that we are feeding to our model. So now if you remember, the features are the number of parameters on which the prediction of our model will be based. So as I had already told you, we are using 5 features, and those are open, high, low, close, and volume. So 1, 2, 3, 4, and 5. And when we had done this data processing, I had also told you that the training data and the validation data will always be two-dimensional arrays, and their shapes will always be in the form of rows cross column. And since they are directly fetched from this CSV file where we have these number of rows and 5 columns, hence the shape of this training data and validation data will also be number of rows into number of columns. However, the number of rows can vary depending upon how we are grouping the data and feeding it to the model, but the number of columns will remain the same, and those will be equal to 5. So we are fetching the data here and we are processing it, and then we have got this training data and validation data, which are two arrays having the shape in the format of number of rows comma number of columns, where the rows and columns belong to our original data set that we have specified in the CSV file. So naturally this will now output the number of columns as I explained you, and so this array here is according to the format that we need, which is batch size first, then time steps, and then finally the number of features. So our training data will be fed to our model through this empty array, which has the required format for LSTM models. So once that is done, we are creating another array and storing it in this variable y. Now this empty array, as you can see, has only two components in its shape, which are length of batch indices and then 1, which means 1 column, and rows will be equal to the number of elements present in the batch indices, and thus this y array will be a two-dimensional array. So now once we are done with creating these empty arrays, we will move forward and fill in the data, or we will populate these arrays with the appropriate data. So for that we will be using a for loop. So this for loop, like every other for loop, first has an integer I, and this I, like in case of every other for loop, will keep the count of which iteration of the loop is running. This IDX here is a variable in which a certain value will be stored, and we are going to enumerate this batch indices array. So the number of times this loop will iterate over these two lines of codes will be equal to the number of elements present in this array. So for each iteration of this for loop, this IDX variable will actually store the value of the element present in the batch indices at the ith index. So let's say that I is 0 for the first iteration of this loop. So the IDX variable will store the value of the 0th element present in the batch indices array. Similarly, if I is 1, then this means that the loop is iterating for the second time and hence the 1th index, and this IDX variable will now store the element which is at the 1th index of this batch indices array. And this will go on till this for loop has iterated over all the elements of the batch indices array. So now once that is done, we can understand what is actually happening inside this for loop. So now here we have taken the ith index of this empty array, and then we are populating it with this line of code. So now again we are taking this data array which we have received while creating this class, and now this X array will be derived from this data array. So first of all, here is a colon. So we are performing slicing on this original data array, and this decides the starting logic of the slicing, and this part here decides the ending logic of the slicing. Now to understand this slicing completely, we will again have to go back to our whiteboard and again try to visualize how this slicing works. So let us say for the first iteration of this loop, this I will be naturally 0, and so we will store something at the 0th index of this X array. So now we have to slice this data array, and for that first we have IDX. So this IDX will be zeroth element of the batch indices array since I is 0. So let us go back to our example, and this is the batch indices array here, as you can see. So at the zeroth index we have the element 0. So here we have 0. So let me write it here. So for the first iteration we have 0, and then we are doing IDX plus self dot time steps to end this slicing. Okay, so let us add the time steps to this 0. So it will be 0 plus 60. So for the first iteration we have here 60. So this is the slicing part of the original data array for the first iteration. So let me write it here 1. Now let us see what will be the slicing part for the second iteration. So now again here we will have 1, and so we will have to find out what is the element present at the first index of this batch indices array. So now as you can see here it is 1. So here we have 1, and then again for the ending part we will have IDX plus self dot time steps. This means that we will have to do 1 plus 60, and then we will have 61. So this will be for our second iteration. Okay, so now let us say that our original data array has the following elements stored in it: 0, 1, 2, 3, 4, and so on and so forth till 60, and then we have 61, 62, 63, and so on and so forth, maybe till 1000. So now this is our original data array, as you can see here. And now let us try to slice it according to the results that we have got over here. So for the first iteration, we have to slice its rows from the 0th index to the 60th index. So now let me assign indices to this original data array. So this 0th element will be present at the 0th index. This 1 element will be present at the first index. This 2 element will be present at the second index, and this 3 element will be present at the third index, and so on and so forth until here. So this 60th element will be present at the 60th index, and following this logic, this 1000th element will be present at the 1000th index. So now when I say that we have to slice this data array from 0 to 60, and that is what we are doing in the first iteration, then that means that we will start from the 0th index and go on till 59th index, and not actually 60th index. So here we have 59, which is the element of this data array, and it is located at the 59th index. So we will start from 0th index and go on till 59th index. Whenever we slice something, the last part of this slicing is always exclusive. So now here in the data array, if you will count the number of elements that we have during our first iteration, it will be equal to 60. Now for the second iteration, we will have to slice this data array starting from 1 to 61. So here is the first index, and then here is the 61st index. So now again, as I told you before, this 61st index will be exclusive, and we will actually go only till the 60th index, that is this one. So we will start from here. First index will be inclusive, but 61st index will be exclusive, and hence we will land up on 60th index. So again, if you will count the number of elements that we have sliced from the data array in this second iteration, then it will again be equal to 60. Now if you have noticed that why we are always getting 60 here, that is because we have defined our time steps to be equal to 60, and hence we are always slicing this data array in such a manner so that we are always getting only 60 elements. So now let's go back to our code. So now you must have understood how we are populating this X array. However, it is very important to note here that we haven't specified here comma and then something. This is because we only want to slice the rows, and we want all the columns, since we will be using the 5 features that I have told you here, which are open, high, low, close, and volume. So we want all these 5 columns. So that's why we haven't specified anything. And that's why in this X array, while populating it, the values of all the columns will be included. However, only the rows will be sliced. Now let us try to understand how we are populating this Y array. So again, we have taken the ith index of this Y array, and then what we have is self.data idx plus self.timesteps comma 3. Now here, as you can see, there is no colon anywhere inside these brackets, and that's why we are not actually slicing this data array here. So instead we are only fetching a particular value from this data array. So now each time this line of code runs inside this loop, it will fetch only one particular value and not number of values from this data array, and it will store at the ith index of this Y array. So now let us understand how we are actually populating this Y array. So now, as you can see, we have specified comma here inside these brackets. So this means that the part before the comma represents the rows, and this means that the part after the comma represents columns. So now, to understand how we are populating this Y array, we will have to replicate the structure of our original data. So as you can see, this original data has n number of rows and it has 5 columns. So open, high, low, close, and volume. It actually has 6 columns if we count the timestamp, but I had already explained it in the previous part that the value of this timestamp is unique for each row, and hence I have considered this timestamp column as index for this complete data set. So actually, when we count columns, we should start from open column and it will be indexed as 0. Then we have high, which will be indexed as 1, and so on and so forth. So let us say that this is our data set. So it has number of rows. So again, let me start from 0, 1, 2, and maybe till 1000 here. So now once that is done, this is the first row. Then again we have the second row. So let me give it a heading. So this is the first row. Then in the second row of our data set, we have, let's say, 1, 2, then 3, and then again till 1000. Similarly, in the third row of our data set, we have again 2, 3, 4, and again till 1000. And so once we have replicated the structure of original data in this example, we can now understand what is happening here. So as you can see, first we have idx plus self.timesteps. So for the first iteration, I will be equal to 0, and this idx variable here will store the 0th element present in the batch indices array. So now, as you can see here, our batch indices array has 0 at the 0th index, and so this idx will store 0 for the first iteration of this for loop. Now we have to do 0 plus self.timesteps. So it will be equal to 0 plus 60, which will give us 60. Now in this data set here, let us say that 60 is present here, which is the element of the data set, and this will naturally have 60th index. So this will have 0th index, this will have first index, this will have second index, and so on and so forth. So now here we have idx plus self.timesteps, which gives us 60. So here is the 60th index. So in this row, we have to look for the third column. So in this row here, we will have third column, and let us say the element present here is 62. So in this row of our data set, which is indexed to be 60th, we have to look for the element in the third column, which is 62. So actually, for the 0th iteration, according to our this example of data set, we will store 62 at the ith position of this Y array. So now if we go back to our original data set here, then we will find out that the column having the third index is actually the column in which the closing prices of the Bitcoin are stored according to their timestamps, which is this column marked by this color. So now let us try to evaluate this first line of code for this for loop on the original data set here. So as I explained you, considering this example data set here, let us try to apply the same logic here. So now, as you can see, this is the first row of our data set and it will be indexed as 0. So now here we will start from 0 and then we will end up on 0 plus self dot time steps, that is 0 plus 60, that is 60. So actually we will not go till the 60th index, but we will end till the 59th index. And let us say for the sake of simplicity that this row here has 59th index. So now when this line of code will be executed for the first time, that is for the first iteration, I will be equal to 0, and hence at the 0th position of this X array, all the data that is present starting from the first row of this data set, that is here, till the 59th index, that is this row here that we have considered to have 59th index. So all the values which are present in this selection will be stored inside this X array at the ith position. However, a warning that the values which are inside this timestamp column wouldn't be stored in this array, X array, as this timestamp column is nothing but index for this original dataset. And this index of the original dataset shouldn't be confused with the index of the data array here, because this data array will be indexed internally and those indices will be normal indices like 0, 1, 2, 3 and so on and so forth, like I was explaining here in all these examples. So now once that is done, let us move forward and understand this line of code on the original dataset. So as I told you that for the first iteration I will be 0. So at the 0th position of the Y array, we have idx plus self dot time steps. This idx, as I told you before, will be 0. So 0 plus self dot time steps. So that will be equal to 60. So here we have to go to the row which has 60th index. So as I told you before, if this row here has 59th index, then naturally this row here will have 60th index. So once we are at the row having the 60th index, we have to look in the third column. So again, this is the 0th column having the open values. This is the first column. This is the second column. And this is the third column. So we have this single value here, which is 16536.69. So only this value 16536.69 will be stored at the ith position, that is at the 0th position of the Y array for the 0th iteration. So again, to sum up, for the 0th iteration, all the values that you can see here from the first row to this row indexed to be 59 will be stored inside the X array at the 0th position, and then this particular value which is stored in this row, which comes just after the last row that was stored in this X array, will be stored inside the Y array again at the 0th position, since I is 0. So now again when I becomes 1, we will leave this first row and we will continue from this row, that is the second row. So this will have the index of 1 and then we will go till here. So now this was the row having the 59th index, as I told you before, and if this is the row having the 59th index, then this will be the row having the 60th index. And why I selected this much slice of the original data set is because for the second iteration, when I will be equal to 1, we will start from 1 and then we will have 1 plus self dot time steps, that is 1 plus 60, which is 61. So we have to start from 1 and then we have to end at the row having the 60th index and not actually the 61st index. And now all the values that you can see here except the values present in this timestamp column will be stored inside the X array at the first index as this I is 1. And once that is done, this line of code here will be executed for the first iteration. So again when I is equal to 1, idx will be equal to 1. So 1 plus self dot time steps, that is 61 and then 3. So now we have to look for the row having the 61st index. So as I told you, this was the row having the 60th index. So naturally this will be the row having the 61st index. And then in that row we have to look for the third column. So this is the third column when the first column is indexed from 0, and this is the value that we want, which is 16531.97. So this will be stored in the first position of this Y array. Then once we have iterated over all the elements present in this batch indices array, we will exit from this loop and then we will return the final X and Y arrays. Now once you have understood the logic of this for loop here, let us understand the purpose of creating these two different arrays, or rather the purpose of this Y array. So now let us say for the first time step, these are the 60 data rows that will be fed to our model. So all these values will be stored in our X array at the 0th position, and once that is done, this for loop will move forward and store this value, which by the way is exactly after the last row of the first time step. So only this closing price here will be stored at the 0th position of our Y array. So now if you connect the dots, for all the data rows belonging to a particular time step, once the data is stored in this X array at the right position, the code stores only the closing price which belongs to the row which is just after the last row that was present in that time step. So this is very important as our model is based on supervised machine learning. So while the training process is going on, after each time step, it will try to apply the information that it has analyzed from the data rows present in that time step on the closing price which is present in this array for that particular time step. So it will try to predict this closing price, and then once it has predicted this closing price, it will look at that particular position in the Y array which contains the actual closing price for that particular timestamp, and then it will try to analyze the difference and what can be done to improve the difference between the price it has predicted and the actual price which is stored in this Y array at that particular position. So once it has analyzed this, the model will consider its analysis and its training process for the next timestamp, that is the next 60 rows, will be affected by the analysis. And this goes on until the model has seen all the data set or it has completed all the epochs. Now whatever I told you just now should not be confused with the validation data. While training process is going on, after each time step, the model will try to predict a single closing price, and then the deviation present between whatever it has predicted and the actual closing price, which it will fetch from this Y array, will affect how the model analyzes the sequences and patterns present in the next time step. However, the validation data contains a number of data points, and it also contains what should be predicted with respect to those data points, and it is passed to the model after the model has seen all the data, that is after a particular epoch has been finished. So whatever analysis that it makes from the deviation present between the predicted values and the actual values present in the validation dataset will affect how it analyzes the sequences and patterns present in the next epoch as a whole. So now, once you have understood how we are feeding the training data to our model, let us move forward and understand how we are feeding the validation data to our model. So again, I have created a variable validation data generator, and this variable stores the object of class training data generator. So as you can see, I am using the same class that I have used for feeding the training data to the model. And to understand why this is so, first we will have to understand what is validation data. So now validation data is actually pretty simple, as it is nothing more than bunch of data rows combined together, which will be fed to our model once an epoch is done while training. So this helps the model to evaluate itself against a data that it has never seen, and thus it knows actually how well it is performing with the sequences and patterns that it has analyzed from the training data. So if we have, let's say, two epochs, then once the first epoch is done, it will process the validation data and make some predictions with the data provided in the validation data, and thus it will know how more effectively it should analyze the sequences and patterns over the next epoch as a whole. So now if you have watched the previous part of the series where I have explained data pre-processing, in that part I have also explained the training and validation split of the data. So of the complete data set, we are taking 85% of the data. Then of that 85%, we are using 90% for training and the rest 10% will be used as the validation data. And it is nothing but a bunch of data rows, as I told you before, and it will be fed to our model after each epoch. So now let us understand how it makes its analysis on the basis of validation data. So it is very simple, and the logic involved in this is really same as what it does to the training data. So here, let us say that these are the first 60 rows of our validation data. So again, these 60 rows will be fed to our model, and since our time step is 60 in this example, we will have the closing price here after the last data row present in the first time step, and then it will try to predict this closing price, and again this closing price here will be stored in the y array at the ith position, and then again it will try to analyze this, and then once it has analyzed, it will move forward and then take the next time step, that is the next 60 data rows, and then again continue this whole process. So here no new logic is applied, and how the model treats the training data, in the same way the model will treat the validation data. Only difference is the deviation that it has found out after each time step will not immediately affect the next time step, as the training process for that particular epoch is completed, and the validation data, as I told you before, is fed after the epoch. So this analysis that it makes from the validation data will affect how the model sees data for yet another time, that is for the next epoch. So since the logic involved and how the model treats the validation data is nearly the same as in case of the training data, hence we are using the training data generator. And as you can see, while making this object, we have passed our parameters here, and we are overriding the default ones. So here first we are passing the training data for our training data generator, and it is already pre-processed in this part of the code here. So now we want 3 workers, as I'm leveraging the power of GPU and CPU as well, and this will spawn 3 parallel processing threads. And then yes, I want to use multi-processing, and then we are passing our batch size and time steps. So this is not 60 and 32 as it was in case of this default ones, but now it will be equal to those that we have specified here. So now our actual batch size is 256 and our actual time steps are 180. So that is what I am passing here. And in a very similar way, we have our validation data generator here. Now all these things are same for the validation data generator, except that we are passing the validation data instead of the training data. So this was all for today's video. In the next video, first we will learn 2 concepts, which are early stopping and model checkpoint. This will help to increase the efficiency of our training process. And then here we will define our model architecture, and then we will try to make predictions with our model. So I know this video was pretty long, but the topic of this video was actually important, as it provides a clever way to feed a very large amount of data into our model in spite of the limitations of the device that we are working on. So thanks for watching, and I will see you again in the next part.